couple of announcements before we get started. So first of all, PS1 is out, problem set 1. It is due on 17th. That's 2 weeks from today. You have exactly 2 weeks to work on it. You can take up to 2 or 3 late days. I think you can take up to 3 late days. There's a good amount of programming and a good amount of math you need to do. So PS1 needs to be uploaded. The solutions need to be uploaded to Gradescope. You'll have to make 2 submissions. One submission will be a PDF file, which you can either use a LaTeX template that we provide, or you can handwrite it as well. But you're strongly encouraged to use the LaTeX template. And there is a separate coding assignment for which you'll have to submit code as a separate Gradescope assignment. So you're going to see 2 assignments in Gradescope. One is for the written part, the other is for the programming part. With that, let's jump right into today's topics. So today we're going to cover briefly. We're going to cover the Perceptron algorithm, and then good chunk of today is going to be exponential family and generalized linear models, and we'll end it with softmax regression for multi-class classification. So Perceptron, we saw in logistic regression. So first of all, the Perceptron algorithm, I should mention, is not something that is widely used in practice. We study it mostly for historical reasons, and also because it's nice and simple, and it's easy to analyze, and we also have homework questions on it. So logistic regression. We saw logistic regression uses the sigmoid function. So the logistic regression uses the sigmoid function, which essentially squeezes the entire real line from -infinity to infinity between 0 and 1, and the 0 and 1 kind of represents the probability, right? You could also think of a variant of that, which will be like the Perceptron, where so in the sigmoid function at z equals 0, g of z is a half, and as z tends to -infinity, g tends to 0, and as z tends to +infinity, g tends to 1. Right? The Perceptron algorithm uses a somewhat similar but different function, which let's say this is z, and right. So g of z in this case is 1 if z is greater than or equal to 0, and 0 if z is less than 0. Right? So you can think of this as the hard version of the sigmoid function, right? And this leads to the hypothesis function here being h theta of x is equal to g of theta transpose x. Right? So theta transpose x. Here theta is the parameter, x is the input, and h theta of x will be 0 or 1, depending on whether theta transpose x was less than 0 or greater than 0. And similarly in logistic regression, we had h theta of x is equal to 1 over 1 plus e to the minus theta transpose x. Yeah, essentially g of z, where g is the sigmoid function. Both of them have a common update rule, which on the surface looks similar. So theta j equal to theta j plus alpha times yi minus h theta of xi times xij. Right? So the update rules for the perceptron and logistic regression, they look the same, except h theta of x means different things in the two different scenarios. We also saw that it was similar for linear regression as well, and we're going to see why this is that this is actually a more common theme. So what's happening here? So if you inspect this equation to get a better sense of what's happening in the perceptron algorithm, this quantity over here is a scalar, right? It's the difference between yi, which can be either 0 and 1, and h theta of xi, which can either be 0 or 1, right? So when the algorithm makes a prediction of h theta of xi for a given xi, this quantity will either be 0 if the algorithm got it right already, right? And it will be either +1 or -1 if the ground truth was +1 and the algorithm predicted 0, then this will evaluate to 1 if wrong and yi equals 1, and similarly it is -1 if wrong and yi is 0. So what's happening here? To see what's happening, it's useful to see this picture. Right? So this is the input space, right? And let's imagine there are two classes, boxes and let's say circles, right? And you want to learn an algorithm that can separate these two classes, right? And if you imagine that the what the algorithm has learned so far is a theta that represents this decision boundary, right? So this represents theta transpose x equals 0, and anything above is theta transpose x is greater than 0, and anything below is theta transpose x less than 0, right? And let's say the algorithm is learning one example at a time, and a new example comes in, and this time it happens to be, the new example happens to be a square or a box, and but the algorithm has misclassified it, right? Now this line, the separating boundary, if the vector equivalent of that would be a vector that's normal to the line. So this would be theta, right? And this is our new x, right? This is the new x. So this got misclassified. This is lying on the bottom of the decision boundary. So what's going to happen here? Yi, let's call this the 1 class, and this as the 0 class, right? So yi minus h theta of I will be +1, right? And what the algorithm is doing is it sets theta to be theta plus alpha times x, right? So this is the old theta, this is x, alpha is some small learning rate, so it adds, let me use a different color here, it adds, right, alpha times x to theta, and now say this is, let's call it theta prime, is the new vector. That's the updated value, right? And the separating hyperplane corresponding to this is something that is normal to it, right? Yeah. So it updated the decision boundary such that x is now included in the positive class, right? The idea here is that theta, we want theta to be similar to x in general, where y is 1, and we want theta to be not similar to x when y equals 0. The reason is when two vectors are similar, the dot product is positive, and they are not similar, the dot product is negative. What does that mean? If let's say this is x, and let's say you have theta, if they're kind of pointed outwards, their dot product would be negative, and if you have a theta that looks like this, let's call it theta prime, then the dot product will be positive if their angle is less than. So this essentially means that as theta is rotating, the decision boundary is kind of perpendicular to theta, and you want to get all the positive x's on one side of the decision boundary. And what's the most naive way of taking theta and given x, try to make theta more kind of closer to x? A simple thing is to just add a component of x in that direction, add it here, and you kind of make theta. And so this is a very common technique used in lots of algorithms, where if you add a vector to another vector, you make the second one kind of closer to the first one, essentially. So this is the perceptron algorithm. You go example by example in an online manner, and if the example is already classified, you do nothing. You get a 0 over here. If it is misclassified, you either add a small component of you add the vector itself, the example itself, to your theta, or you subtract it, depending on the class of the vector. That's about it. Any questions about the perceptron? Cool. So let's move on to the next topic. Exponential families. So exponential family is essentially a class of, yeah. It's not used in practice because it does not have a probabilistic interpretation of what's happening. You kind of have a geometrical feel of what's happening with the hyperplane, but it doesn't have a probabilistic interpretation. Also, it was I think the perceptron was pretty famous in, I think, the 1950s or the 60s, where people thought this is a good model of how the brain works. And I think it was Marvin Minsky who wrote a paper saying, the perceptron is kind of limited because it could never classify points like this. And there's no possible separating boundary that can do something as simple as this, and kind of people lost interest in it. But yeah. And in fact, what we see is in logistic regression is like a softer version of the perceptron itself in a way. Yeah. Yeah. It's up to it's a design choice that you make. What you could do is you can kind of anneal your learning rate with every step. Every time you see a new example, decrease your learning rate until something until you stop changing theta by a lot. You're not guaranteed that you'll be able to get every example right. For example, here, no matter how long you learn, you're never going to find a learning boundary. So it's up to you when you want to stop training. A common thing is to just decrease the learning rate with every time step until you stop making changes. Right, let's move on to exponential families. So exponential families is a class of probability distributions which are somewhat nice mathematically, right? They're also very closely related to GLMs, which we will be going over next. Right? But first we'll kind of take a deeper look at exponential families and what they're about. So an exponential family is one whose PDF So whose PDF can be written in the form, by PDF I mean probability density function. If it's a discrete distribution, then it would be the probability mass function. Right? Whose PDF can be written in the form This looks pretty scary. Let's kind of break it down into what they actually mean. So Y over here is the data, right? And there is a reason why we call it Y, because a bit larger, sure. Is it better? Yeah. So Y is the data, and there's a reason why we call it Y and not X, and that's because we're going to use exponential families to model the output of your data, in a supervised learning setting, and we're going to see X when we move on to GLMs. Until then, we're just going to deal with Y's for now. So Y is the data. Eta is called the natural parameter. Right? T of Y is called a sufficient statistic. If you have a statistics background and if you come across the word sufficient statistic before, it's the exact same thing. But you don't need to know much about this, because for all the distributions that we're going to be seeing today or in this class, T of Y will be equal to just Y. So you can just replace T of Y with Y for all the examples today and in the rest of the class. B of Y is called a base measure. Right? And finally, A of eta is called the log partition function. And we're going to be seeing a lot of this function, log partition function. Right? So again, Y is the data that this probability distribution is trying to model. Eta is the parameter of the distribution. T of Y, which will mostly be just Y. Technically, T of Y is more correct. B of Y, which means it is a function of only Y. This function cannot involve eta, right? And similarly, T of Y cannot involve eta. It should be purely a function of Y. B of Y is called the base measure, and A of eta, which has to be a function of only eta and constants. No Y can be part of A of eta. It's called the log partition function, right? And the reason why this is called the log partition function is pretty easy to see, because this can be written as B of Y E x of eta transpose T of Y. So these two are exactly the same. Just take this out and sorry, this should be the log. I think it's fine. Right, these two are exactly the same, and oh yeah, you're right. This should be positive. Thank you. So this is, you can think of this as a normalizing constant of the distribution, such that the whole thing integrates to 1, right? and therefore the log of this will be a of eta. That's why it's just called the log of the partition function. So the partition function is a technical term to indicate the normalizing constant of probability distributions. Now, you can plug in any definition of B, A, and T. Yeah. Sure. So y is your y, and for most of our example, it's going to be a scalar. Eta can be a vector, but we will also be focusing, except maybe in softmax, this would be a scalar. T of y has to match. So the dimension of these two has to match. And these are scalars. Right? So for any choice of A, B, and T that can be your choice completely, as long as the expression integrates to 1, you have a family in the exponential family. Right? What does that mean? For specific choice of for some choice of A, B, and T, this will be equal to, say, the PDF of the Gaussian. In which case you got for that choice of T, A, and B, you got the Gaussian distribution, a family of Gaussian distribution, such that for any value of the parameter, you get a member of the Gaussian family. Right? And this is mostly to show that a distribution is in the exponential family. The most straightforward way to do it is to write out the PDF of the distribution in the form that you know, and just do some algebraic massaging to bring it into this form, right? And then you do a pattern match to conclude that it's a member of the exponential family. So let's do it for a couple of examples. So we have a Bernoulli distribution is one used to model binary data, right? And it has a parameter, let's call it phi, which is the probability of the event happening or not, right? Right. Now the what's the PDF of a Bernoulli distribution? One way to write this is phi of y times 1 minus phi 1 minus y. Does it make sense? This pattern is like a way of writing a programmatic if-else in math, right? So whenever y is 1, this term cancels out, so the answer would be phi, and whenever y is 0, this term cancels out, and the answer is 1 minus phi. So this is just a mathematical way to represent an if-else that you would do in programming, right? So this is the PDF of a Bernoulli, and our goal is to take this form and massage it into that form, right? And see what the individual T, B, and A turn out to be, right? So whenever you see a distribution in this form, a common technique is to wrap this with a log and an exp, right? Because these two cancel out, so this is actually exactly equal to this. And if you do some more algebra on this, we will see that this turns out to be exp of log phi over 1 minus phi times y plus log of 1 minus phi. Right? it's pretty straightforward to go from here to here. I'll let you guys verify it yourself. But once we have it in this form, it's easy to kind of start doing some pattern matching from this expression to that expression. So what we see here is the base measure b of y is equal to, if you match this with that, b of y will be just 1 because there's no b of y term here, right? And so this would be b of y. This would be eta. This would be t of y. This would be a of eta, right? So that would be, you can see that, they kind of match in pattern. So b of y would be 1. T of y is just y, as as expected. What else? So eta is equal to log phi over 1 minus phi, right? And this is an equivalent statement is to invert this operation and say phi is equal to 1 over 1 plus e to the minus eta, right? I'm just flipping the operation from this went from phi to eta. Here, it's the equivalent. Now here it goes from eta to phi, right? And a of eta is going to be, so here we have it as a function of phi, but we got an expression for phi in terms of eta. So you can plug this expression in here and with a change of minus sign. So let me work out this. So it's going to be minus log of 1 minus phi. Now this is, I just did pattern matching there, and minus log 1 minus this thing over here, 1 over 1 plus e to the minus eta. The reason is because we want an expression in terms of eta. Here we got it in terms of phi, but we need to plug in eta over here. Eta, and this will just be log of 1 plus e to the eta. Right? So there you go. So this kind of verifies that the Bernoulli distribution is a member of the exponential family. Any questions here? So note that this might look familiar. It looks like the sigmoid function, somewhat like the sigmoid function, and this is actually no accident. We'll see why it is actually the sigmoid, how it kind of relates to logistic regression in a minute. So another example. So a Gaussian with fixed variance. Right. So a Gaussian distribution has two parameters, the mean and the variance. For our purposes, we are going to assume a constant variance. You can have you can also consider Gaussians with where the variance is also a variable, but for our course, we're only interested in Gaussians with fixed variance, and we are going to assume that variance is equal to 1. So this gives the PDF of a Gaussian to look like this: P of y parameterized as mu. So note here, when we start writing out, we start with the parameters that we are commonly used to. They are also called like the canonical parameters. And then we set up a link between the canonical parameters and the natural parameters. That's part of the massaging exercise that we do. Right? So we're going to start with the canonical parameters. Is equal to 1 over root 2 pi over 2. So this is the Gaussian PDF with variance equal to 1, right? And this can be rewritten as, again, I'm skipping a few algebra steps, straightforward, no tricks there. Any question? Yeah. Oh, fixed variance. E to the minus y square over 2 times ex. Right. Again, we go through the same exercise, pattern match. This is b of y, right? This is eta, this is t of y, and this would be a of eta. Right? So we have b of y equals 1 over root 2 pi minus y square by 2. Note that this is a function of only y, there's no eta here. T of y is just y, and in this case, natural parameter is mu, eta is mu, and the log partition function is equal to mu square by 2, and when we repeat the same exercise we did here. We start with a log partition function that is parameterized by the canonical parameters, and we use the link between the canonical and the natural parameters, invert it, and so in this case it's the same. So it's eta over 2. So a of eta is a function of only eta. Again here, a of eta was a function of only eta, and t of y is a function of only y, and b of y is a function of only y as well. Any questions on this? Yeah. Yeah, if the variance is unknown, you can write it as an exponential family, in which case eta will now be a vector. It won't be a scalar anymore. It'll have two, like eta 1 and eta 2, and you will also have a mapping between each of the canonical parameters and each of the natural parameters. You can do it. No, it's pretty straightforward. Right. So this is exponential. These are exponential families, right? The reason why we use exponential families is because it has some nice mathematical properties. Right. So one property is now if we perform maximum likelihood on the exponential family when the exponential family is parameterized in the natural parameters, then the optimization problem is concave. So MLE with respect to eta is concave. Similarly, if you flip the sign and use the what's called the negative log likelihood, so take the log of the expression, negate it, and in this case, the negative log likelihood is like the cost function equivalent of doing maximum likelihood. So you're just flipping a sign. Instead of maximizing, you minimize the negative log likelihood. So the NLL is therefore convex. Right? There's the expectation of y what does this mean? Each of the distribution, we start with a of eta, differentiate this with respect to eta, the log partition function with respect to eta, and you get another function with respect to eta, and that function is the mean of the distribution as parameterized by eta. Right? And similarly, the variance of y parameterized by eta is just the second derivative. This was the first derivative, this is the second derivative. This is eta. So the reason why this is nice is because in general for probability distributions to calculate the mean and the variance, you generally need to integrate something. But over here you just need to differentiate, which is a lot easier operation. And you will be proving these properties in your first homework. We provided hints, so it should be. Right. So now we're going to move on to generalized linear models. This is all we want to talk about exponential families. Any questions? Yeah.
If you were doing like a multivariate Gaussian, would eta include like the covariance matrix?
Exactly. So if it's a multivariate Gaussian, then this eta would be a vector, and this would be the Hessian. All right, let's move on to GLMs. So the GLM is somewhat like a natural extension of the exponential families to include covariates or include your input features in some way, right? So over here we are only dealing with in the exponential families you're only dealing with like the y, which in our case it'll kind of map to the outputs, but we can actually build a lot of many powerful models by choosing an appropriate family in the exponential family and kind of plugging it onto a linear model. So the assumptions we are going to make for GLM is that one, so these are the assumptions or design choices that are going to take us from exponential families to generalized linear models. So the most important assumption is that, assumption is that y given x parameterized by a theta is a member of an exponential family by exponential family of eta, I mean that form. It could in the particular scenario that you have, it could take on any one of these distributions. We only talked about the Bernoulli and Gaussian. There are also other distributions those are part of the exponential family. For example, I forgot to mention this. So if you have real valued data, you use a Gaussian. If you have binary, you have Bernoulli. If you have counts, by counts here, so this is real valued. It can take any value between 0 and infinity. By count, it means just non-negative integers, but not anything in between. So if you have counts, you can use a Poisson. If you have positive real valued integers, like say the volume of some object or the time to an event, which where you're only predicting into the future. So here you can use like gamma or exponential. So there is the exponential family, and there is also a distribution called the exponential distribution, which are two distinct things. The exponential distribution happens to be a member of the exponential family as well, but they're not the same thing. The exponential and and you can also have probability distributions over probability distributions. Like beta, the Dirichlet. These mostly show up in Bayesian machine learning or Bayesian statistics. Right. So, depending on the kind of data that you have, if your y variable is if you're trying to do a regression, then your y is going to be, say a Gaussian. If you're trying to do a classification, then your y is, if it's a binary classification, then the exponential family would be Bernoulli. So depending on the problem that you have, you can choose any member of the exponential family as parameterized by eta. And so that's the first assumption, that y condition on y given x is a member of the exponential family. And the second, the design choice that we are making here is that eta is equal to theta transpose x. So this is where your x now comes into the picture, right? So theta is in Rn, and x is also in Rn. Now this n has nothing to do with anything in the exponential family. It's purely the dimensions of your data that you have, the x's of your inputs, and this does not show up anywhere else. Right? That's eta is we make a design choice that eta will be theta transpose x. And another kind of assumption is that at test time, right, when we want to output for a new x, given a new x, we want to make an output, right? So the output will be right. So given an x and given an x, we get an exponential family distribution, right? And the mean of that distribution will be the prediction that we make for a given x. This may sound a little abstract, but we're going to make this more clear. So what this essentially means is that the hypothesis function is actually just right. This is our hypothesis function, and we'll see that what we do over here. If you plug in the exponential family as Gaussian, then the hypothesis will be the same Gaussian hypothesis that we saw in linear regression. If we plug in a Bernoulli, then this will turn out to be the same hypothesis that we saw in logistic regression, and so on. Right. So one way to kind of visualize this is right. So one way to think of this is there is a model and there is a distribution, right? So the model, we are assuming it to be a linear model, right? Given x, there is a learnable parameter theta, and theta transpose x will give you a parameter, right? This is the model, and here is the distribution. Now the distribution is a member of the exponential family, and the parameter for this distribution is the output of the linear model. Right? This is the picture you want to have in your mind. And the exponential family we make depending on the data that we have, whether it's a classification problem or a regression problem or a time to event problem, you would choose an appropriate B, A, and T based on the distribution of your choice. Right? So this entire thing, and from this you can say get the expectation of y given eta, and this is the same as expectation of y given theta transpose x, right? And this is essentially our hypothesis function. That's exactly right. So the question is, are we training theta to predict the parameter of the exponential family distribution whose mean is the prediction that we're going to make for y? That's correct, right? And so this is what we do at test time, right? And during train time, how do we train this model? So in this model, the parameter that we are learning by doing gradient descent are these parameters, right? So we're not learning any of the parameters in the exponential family. We're not learning mu or sigma square or eta. We're not learning this. We are learning theta. That's part of the model and not part of the distribution. And the output of this will become the distributions parameter. It's unfortunate that we use the word parameter for this and that, but it's important to understand what is being learned during training phase and what's not. Right? So this parameter is the output of a function. It's not a variable that we do gradient descent on. So during learning, what we do is maximum likelihood, maximize with respect to theta log p of y I given right. So we are doing gradient ascent on the log probability of y, where the natural parameter was reparameterized with a linear model, right? And we are doing gradient ascent by taking gradients on theta. Right? This is like the big picture of what's happening with GLMs and how they kind of are an extension of exponential families. You reparameterize the parameters with a linear model and you get a GLM. So let's look at some more detail on what happens at train time. So another kind of incidental benefit of using GLMs is that at train time, we saw that we want to do maximum likelihood on the using the log probability with respect to thetas. Right? Now, at first, it may appear that we need to do some more algebra, figure out what the expression for p is, represent it as a function of theta transpose x, and take the derivatives, and come up with a gradient update rule, and so on. But it turns out that no matter what kind of GLM you're doing, no matter which choice of distribution that you make, the learning update rule is the same. The learning update rule is theta equals theta j plus alpha times yi minus h theta of xi. You guys have seen this so many times by now. So this is, you can straight away just apply this learning rule without ever having to do any more algebra to figure out what the gradients are or what the loss is. You can go straight to the update rule and do your learning. You plug in the appropriate h theta of x, plug in the appropriate h theta of x, depending on the choice of distribution that you make, and you can start learning. Initialize your theta to some random values, and you can start learning. So, any question on this? Yeah. You can do, if you want to do it for batch gradient descent, then you just sum over all your examples. Yeah, so the Newton method is probably the most common you would use with GLMs, and that again comes with the assumption that the dimensionality of your data is not extremely high. As long as the number of features is less than a few thousand, then you can do Newton's method. Any other question? Cool. So, so this is the same update rule for any specific type of GLM based on the choice of distribution that you have. Whether you're modeling, you're doing classification, whether you're doing regression, whether you're doing, a Poisson regression, the update rule is the same. You just plug in a different h theta of x, and you get your learning rule. Another, some more terminology. So eta is what we call the natural parameter. Okay. So eta is the natural parameter, and the function that links the natural parameter to the mean of the distribution, and this has a name. It's called the canonical response function. Right? And similarly, you can also, let's call it mu. It's like the mean of the distribution. Similarly, you can go from mu back to eta with the inverse of this. And this is also called the canonical link function. This is some terminology. We also already saw that g of eta is also equal to the gradient of the log partition function with respect to eta. So a side note, g is equal to and it's also helpful to make explicit the distinction between the three different kinds of parameterizations we have. So we have three parameterizations. So we have the model parameters, that's theta, the natural parameters, that's eta, and we have the canonical parameters. And this is, say, phi for Bernoulli, mu and sigma square for Gaussian, lambda for Poisson. Right? So these are three different ways we can parameterize either the exponential family or the GLM. And whenever we are learning a GLM, it is only this thing that we learn. Right? That is the theta in the linear model. This is the theta that is learned. Right? And the connection between these two is linear. So theta transpose x will give you the natural parameter. And this is the design choice that we're making. Right? We choose to reparameterize eta by a linear model, a linear in your data. And between these two, you have G to go this way and G inverse to come back this way, where G is also the derivative of the log partition. So yeah, so it's important to kind of realize, it can get pretty confusing when you're seeing this for the first time, because you have so many parameters that are being swapped around and getting reparameterized. There are three kind of spaces in which, three different ways in which we are parameterizing generalized linear models. The model parameters, the ones that we learn, and the output of this is the natural parameter for the exponential family, and you can do some algebraic manipulations and get the canonical parameters for the distribution that we are choosing, depending on the task, whether it's classification or regression. Any questions on this? So now it's actually pretty, you can see, when you're doing logistic regression, right? So h theta of x, is the expected value of y condition x theta, and this is equal to phi, right? Because here the choice of distribution is a Bernoulli, and the mean of a Bernoulli distribution is just phi, in the canonical parameter space. And if we write that as in terms of the e to the minus eta, and this is equal to 1 over minus theta transpose x. Right? So the logistic function, which when we introduced linear logistic regression, we just pulled out the logistic function out of thin air and said, hey, this is something that can squash minus infinity to infinity between 0 and 1. Seems like a good choice. But now we see that it is a natural outcome. It just pops out from this more elegant generalized linear model, where if you choose Bernoulli to be the distribution of your output, then the logistic regression just pops out naturally. So, any questions? Yeah.
Maybe speak a little bit more about choosing a distribution to be the output.
Yeah. So the choice of what distribution you're going to choose is really dependent on the task that you have. So if your task is regression, where you want to output real valued numbers like price of the house or something, then you choose a distribution over the real numbers, like a Gaussian. If your task is classification, where your output is binary 0 or 1, you choose a distribution that models binary data, right? So the task, in a way, influences you to pick the distribution, and most of the times that choice is pretty obvious. If you want to model the number of visitors to a website, which is like a count, you want to use a Poisson distribution, because Poisson distribution is a distribution over integers. So the task pretty much tells you what distribution you want to choose, and then you do the you do this you go through this machinery of figuring out what are the what h theta of x is, and you plug in h theta of x over there, and you have your learning rule. Any more questions? So so we made some assumptions. These assumptions. Now, it's also helpful to kind of get a visualization of what these assumptions actually mean, right? So to expand upon your point, if you think of the question, are GLMs used for classification, or are they used for regression, or are they used for something else? The answer really depends on what is the choice of distribution that you're going to choose. GLMs are just a general way to model data, and that data could be binary, it could be real valued, and as long as you have a distribution that can model that kind of data and falls in the exponential family, it can be just plugged into a GLM and everything just works out nicely. So so the assumptions that we made, let's start with regression. Right? So for regression, we assume there is some x. To simplify, I'm drawing x as one dimension, but x could be multidimensional, and there exists a theta, right? And theta transpose x would be some linear hyperplane, and this we assume is eta, right? And in case of regression, eta was also mu. So eta was also mu. Right? And then we are assuming that the y for any given x is distributed as a Gaussian with mu as the mean. So which means for every x, every possible x, you have the appropriate eta, and with this as the mean, let's think of this as y. So there is a Gaussian distribution at every possible. We assume a variance of 1. So this is like a Gaussian with standard deviation or variance equal to 1. Right? So for every possible x, there is a y given x, which is parameterized by theta transpose x as the mean. Right? And you assume that your data is generated from this process. Right? So what does it mean? It means you're given x, and let's say this is y. So you would have examples in your training set that may look like this. Right? The assumption here is that for every x, there is, let's say for this particular value of x, there was a Gaussian distribution that started with a mean over here, and from this Gaussian distribution, this value was sampled. Right? You're just sampling it from that distribution. Now, this is how your data is generated. Again, this is our assumption. Right? Now, based on these assumptions, what we are doing with the GLM is we start with the data. We don't know anything else. We make an assumption that there is some linear model from which the data was generated in this format. And we want to work backwards, right, to find theta that will give us this line. Right? So for a different choice of theta, we get a different line. Right? We assume that if that line represents the mu's or the means of the y's for that particular x from which it's sampled from, we are trying to find a line which will be like your theta transpose x, from which these y's are most likely to have sampled. That's essentially what's happening when you do maximum likelihood with a GLM. Right? Similarly, for classification, again, let's assume there's an x, right? And there is some theta transpose x, right? And this theta transpose x is eta. We assign this to be eta, right? And this eta is from this eta we run this through the sigmoid function. 1 over 1 plus e to the minus eta to get phi. Right? So if these are the etas for each eta, we run it through the sigmoid, and we get something like this. Right? So this tends to 1, this tends to 0, and when at this point, when eta is 0, the sigmoid is 0.5. Right? This is 0.5. Right? And now, at each point, at any given choice of x, we have a probability distribution. In this case, it's a binary. So let's assume probability of y is the height till the sigmoid line, and here it is low. So at every x, we have a different Bernoulli distribution, essentially, that's obtained where the probability of y is the height to the sigmoid through the natural parameter. And from this, you have a data generating distribution that would look like this. So x, and you have a few x's in your training set, and for those x's, you figure out what your y distribution is and sample from it. So let's say right, and now again our goal is to start given this data. Okay, so over here this is the x and this is y. So these are points for which y is 0. These are points for which y is 1. And so given this data, we want to work backwards to find out what theta was. What's the theta that would have resulted in a sigmoid-like curve from which these y's were most likely to have been sampled? And figuring out that y is essentially doing logistic regression. Any questions? All right, so in the last 10 minutes or so, we will go over softmax regression. So softmax regression is, so in the lecture notes, softmax regression is explained as yet another member of the GLM family. However, in today's lecture, we'll be taking a non-GLM approach and kind of seeing and see how softmax is essentially doing what's also called as cross-entropy minimization. We'll end up with the same formulas and equations. You can go through the GLM interpretation in the notes. It's a little messy to kind of do it on the whiteboard. So whereas this has a nicer interpretation, and it's good to kind of get this cross entropy interpretation as well. So let's assume. So here we are talking about multi-class classification. So let's assume we have three classes of data. Let's call them circles, squares, and say triangles. Now, if here this is x1 and x2. We are just visualizing your input space, and the output space y is kind of implicit in the shape of this. So, in multi-class classification, our goal is to start from this data and learn a model that can, given a new data point, make a prediction of whether this point is a circle, square, or a triangle, right? We're just looking at 3 because it's easy to visualize, but this can work over thousands of classes. So what we have is, we have xi's in Rn, right? So the label y is 0, 1, k. So k is the number of classes. Right? So the labels y is a one hot vector. What you call it is a one hot vector, where it's a vector which indicates which class the x corresponds to. So each element in the vector corresponds to one of the classes. So this may correspond to the triangle class, circle class, square class, or maybe something else. So the labels are in this one hot vector, where we have a vector that's filled with zeros except with a 1 in one of the places. Right? And the way we're going to think of softmax regression is that each class has its own set of parameters. So we have theta class, right, in Rn, and there are k such things where class is in triangle, circle, square, etc. Right? So in logistic regression, we had just one theta, which would do a binary, yes versus no. In softmax, we have one such vector of theta per class. Right? So you could also optionally represent them as a matrix, right, as an n by k matrix, where you have a theta class, right? So in softmax regression, it's a generalization of logistic regression, where you have a set of parameters per class, right? And we're going to do something similar to so all right, let me also so corresponding to each class of parameters, there exists so there exists this line which represents, say, theta triangle transpose x equals 0, and anything to the left will be theta triangle transpose x is greater than 0, and over here it will be less than 0. Right? So if for the theta triangle class, there is this line which corresponds to theta transpose x equals 0. Anything to the left will give you a value greater than 0. Anything to the right. Similarly, there is also so this corresponds to theta square transpose x equals 0. Anything below will be greater than 0. Anything above will be less than 0. And similarly, you have another one for this corresponds to theta circle transpose x equals 0, and this half plane we have it to be greater than 0, and to the left it is less than 0. Right? So we have a different set of parameters per class, which hopefully satisfies this property. And now our goal is to take these parameters, and let's see what happens when we feed a new example. So given an example x, we get a set of given x, and over here we have classes. Right? So we have the circle class, the triangle class, the square class. Right? So over here we plot theta class transpose x. So we may get something that looks like this. So let's say for a new point x over here, if that's our new x, we would have theta transpose theta square transpose x to be positive. So right, and maybe for the others we may have some negative, and maybe something like this for this. Right. So this space is also called the logit space. Right. So these are real numbers. Right. This is not a value between 0 and 1. This is between plus infinity and minus infinity. Right. And our goal is to get a probability distribution over the classes. And in order to do that, we perform a few steps. So we exponentiate the logits, which would give us, so now it is x buff theta class transpose x. And this will make everything positive. So this will be a small squares, triangles, and circles. Right? Now we got a set of positive numbers, and next we normalize this. By normalize, I mean divide everything by the sum of all of them. So here we have theta e to the theta class transpose x over the sum of I in triangle, square, circle, e to the theta I transpose x. So once we do this operation, we now get a probability distribution. Where the sum of the heights will add up to 1. Right? So, if given a new point x and we run through this pipeline, we get a probability output over the classes for which class that example is most likely to belong to, right? And this whole process, so let's call this p hat of y for the given x. Right? So this is like our hypothesis. The output of the hypothesis function will output this probability distribution. In the other cases, the output of the hypothesis function generally output a scalar or a probability. In this case, it's outputting a probability distribution over all the classes. And now, the true y would look something like this. Right? Let's say the point over there was, let's say it was a triangle for whatever reason. Right? If that was the triangle, then the p of y, which is also called the label, you can think of that as a probability distribution, which is 1 over the correct class and 0 elsewhere. Right? So p of y. This is essentially representing the one-hot representation as a probability distribution. Right? Now, the goal or the learning approach that we're going to do is, in a way, minimize the distance between these two distributions. Right? This is one distribution, this is another distribution. We want to change this distribution to look like that distribution. Right? Technically, the term for that is minimize the cross entropy between the two distributions. So the cross entropy between p and p hat is equal to for y in circle, triangle, square, p of y times log p hat of y. I don't think we'll have time to go over the interpretation of cross entropy, but you can look that up. So here we see that P of y will be 1 for just one of the classes and 0 for the others. So let's say in this example, P of, so y was say a triangle. So this will essentially boil down to, so there's a minus log P hat of y triangle, right? And what we saw that this, the hypothesis is essentially that expression. So that's equal to minus log x e x perf theta triangle transpose x over sum of class in triangle square circle e to the angle, right? And on this you treat this as the loss and do gradient descent. Gradient descent with respect to the parameters, right? Yeah, with that, I think any questions on softmax? Okay, so we'll break for today in that case.